Let's talk about actually evaluating some of these probabilities then that are encountered in a binomial experiment. So the outcomes of a binomial experiment fit what's known as the binomial probability distribution. Of course, the random variable x, as previously defined, is the number of successes obtained in the n trials. And we write x is b and p, and that's read as x as a random variable with a binomial distribution. So the binomial distribution function, the mathematical expression for it is, so this is the probability that the random variable x is equal to a particular value x. It's given by n choose x times the probability of success to the x power times the probability of failure to the n minus x power. N choose x is equal to n factorial over the quantity n minus x factorial over x factorial. Now, you can show that the mean and variance, there are neat closed form expressions for both of these, and they can be shown to be equal to, the mean is equal just to NP. So again, for what that would say for the mean, in 100 tosses of a fair coin then, where n is 100 and p is 0.5, we would expect the mean number of heads to be 100 times 0.5 or 50. So on average, we should get 50 heads when we're tossing 100 coins. The variance is equal to n times p times q. So again, in that 100 toss case, p and q would both be 0.5, so the product would be 0.25, and the variance then would be 25. The standard deviation is the square root of the variance, so the standard deviation in that case would be 5. So again, based on our rule of thumb, when we expect the random variable to be within 2 standard deviations of the mean, 2 standard deviations would be 10, the mean is 50. So we would expect when we're carrying out this experiment that most of the time, 95% of the time, we're going to see between 40 and 60 heads tossed then. Now in Octave, you can use of course, you can evaluate this on your calculator. In Octave, you may have a calculator that actually has this PDF function built into it. In Octave, you can use the bino PDF function to find the probability that x is equal to x. It takes 3 arguments: the value of x, the number of trials, and the probability of success. So going back to the dice experiment, to find the probability that you get 4 ones in 10 tosses of the die, where the probability of success is 1 in 6, that probability is 0.05. So only 54 times out of 1,000 are you going to actually get exactly, on average, are you going to get exactly 4 ones when you throw the dice 6 times. To find the probability that x is greater than 3, we could actually add bino PDF of 4 plus bino PDF of 5, 6, 7, 8, 9, and 10. So we could call this function, 6 different times. Alternatively, if you call bino PDF with a vector, here going from 4 to 10, it will return a vector of those values. The binomial PDF evaluated at 4, 5, 6, 7, 8, 9, and 10. That will be a vector. So if we sum those, we'll get all those probabilities. The probability that x is equal to 4, 5, 6, 7, 8, or 9, and 10. Of course, that is equal to the probability that x is greater than 3. And that turns out to be 0.069. So about 7 times out of 10, you're going to throw, you're going to get more than 3 ones in this experiment. 4, 5, 6, 7, 8, or 9, 10, 9 or 10 ones. Okay. Now the cumulative distribution function tends to be much more useful than the probability distribution function, or PDF. So the cumulative distribution function is known as the CDF. It's defined as the probability that x is less than or equal to some particular value. So you can evaluate it from the PDF. It would be the sum of all the PDF values for x taking on the values of, or from 0, or dummy value taking on the values from 0 up to x. Okay, so it seems like the CDF wouldn't be as useful, but it is actually, once you gain a little experience with it, you can evaluate probabilities just like for the PDF, but in addition, it makes it much easier to find the answers to questions about, is x less than or equal to some value, or is x greater than some value. Those are all easily answered using the CDF. Unfortunately, for the binomial distribution, there is no closed form simple formula for the CDF. You can evaluate it in octave. There's a bino-CDF function. Many calculators might have it, but it's typically evaluated using a table lookup method. And on the Fundamentals of Engineering exam, it contains only CDF tables for several distributions. You're not allowed to use any of the calculators that have the CDF function built into it. So we're going to use that table from the manual, and this is the only reference you'll be allowed to use on exams in this course. The table's a little limited. It only it covers trials up to n equal to 20, so you couldn't actually use it for that coin toss experiment where we tossed 100 coins, for example. On that case, you'd have to turn to something like octave. So that means on the exam, I will only give you problems which you can find in this table. So you'll find a link to this table under the lectures link for today's Engineering 390 lecture. So download that, print that out. We'll be using that in an example in just a few minutes. The CDF has the following properties. So you can use it to determine probabilities, just like the probability that x is equal to 4. That's going to be the probability that x is less than 4 minus the probability that x is less than or equal to 3, right? Probability x is less than or equal to 4 minus the probability x is less than or equal to 3. That's going to give you the probability that x is equal to 4. Similarly, the probability that x is greater than 4 is going to be 1 minus the probability x is less than or equal to 4. The probability that x is greater than or equal to 4 is 1 minus the probability x is less than or equal to 3. So watch out for those greater than or greater than to equal things. They're they're a little different, but they should make sense. So again, in octave, you can use the bino-CDF to find the probability that x is less than x, and then some particular value of x. It takes 3 arguments, x, n, and p, just like bino-PDF, but it's a different function. It gives you the probabilities that the random variable is less than or equal to this value. So for example, previously we found the probability that x is equal to 4 in the dice experiment by directly calling bino-PDF with an argument of 4. Here we want to find the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 3. This will give us the probability that x is exactly equal to 4. And this is the same value that we got before. Now to find the probability that x is greater than 3, we'll subtract from 1 the probability that x is less than or equal to 3. So here, for these types of probabilities, the CDF is much easier to use. And we get immediately the 0.069728 value that we had previously. Here's a final example. I'll pull up this table to answer this in just a second. If you've downloaded the table, pause the video, try to use the table to answer these questions, and then come back and restart the video. So consider tossing a loaded coin where the probability of head is equal to 0.6 10 times. We're interested now in our random variable is the number of times tails occurs. So the probability of tails will be our success variable because that's what we're interested in. So it does, don't think of heads as always being success and tails always being failures. A failure in the binomial experiment, our success is what's our random variable of interest. Okay. And then here I'm asking you to use the CDF table that you can download from the website to find the probability that you throw 3 tails, that you throw 3 or fewer tails, or that you throw more than 5 tails in any and tossing this loaded coin 10 times. And then also ask you to find the mean and standard deviation. Use the table to find all probabilities. So pause the video, look at the reference table either on your computer and work these out, or print it out and see if you can find these probabilities. So pause the video, and I'll pause just a second and then continue on. Okay. So I'm back. So in this particular experiment, now n is equal to 10. That's the number of times we're tossing the coin. Our probability of success is 0.4. That's the probability that we throw a tail. Okay, so for the probability that x is equal to 3, we want to look at the probability x is less than or equal to 3 minus the probability x is greater than, less than or equal to 2. So if you flip over to the table, let me pull it up. You know, the table looks like this. What we want to do is over here in this column is n, okay, and then you know, when n is equal to 5, x can take on the values from 0 up to 5, and then p goes, they have different values of p here between 0.1 up to 0.9, and also include 0.95 and 0.99. Now in our problem, we're looking for n equal to 10. That's actually on the second page. Our probability of success is 0.4. And we were going to subtract. We wanted to find the probability that x is equal to 3. So we're going to find the probability that x is less than or equal to 3. That's 0.3823. And subtract the probability that x is equal to 2. That's the 0.1673 here. I realize you can't see my mouse. Let's see if I can actually highlight this. Yeah, I think I can. So 0.4 x equal to 3 is right there. Okay, and then we're going to subtract from that the x is less than or equal to 2, which is right there. So going back to the slide, you can see that's what we did, and that probability that x is equal to 3 is 0.2150 then. The probability x is less than or equal to 3, that's given directly in our table. Okay, that's what these numbers represent. The probability that x is less than x. The random variable is less than a particular value x. So we just read that out right out of the table. Now what about the probability x is greater than 5? That's going to be 1 minus the probability x is less than or equal to 5. So we go back to our table, n equal to 10, look up 5. We find here the 0.8338. So we're going to subtract that from 1 to get the 0.1662. And then we're also asked to find the mean. Theoretically, that's equal to just n times p. Our probability of throwing a tail is 0.4. So in 10 tosses, again, this is a loaded coin. It's not a fair coin. So the probability of getting, or the expected value, the expected number of tails we would get in tossing this coin 10 times is 4 tails. Similarly for the variance, that's NPQ, and that turns out to be, I left out an equal sign here on my slide, that turns out to be equal to 2.4. The standard deviation is going to be the square root of that 2.4, and that's the 1.549. So that's it for the lecture, kind of short and sweet. I'll get these videos up on the lectures link. You'll also find today's homework assignment on there as well. The weather forecast still looks bad, so I'm hoping to see you in class on Wednesday, but if not, I'll post another lecture for you to watch on Wednesday. Have a good evening.